Hello, my name is Christopher Cole with Wolfram Research. My talk is extending the front end with LibraryLink. In my talk, we will learn about how to extend the front end in a modular way, which minimizes inter-process communication. Good afternoon. My name is Christopher Cole. I'm a user interfaces developer at Wolfram Research. In this talk, we'll be discussing how we can extend the front end to, we're going to discuss how the front end using LibraryLink, okay? So the abstract says that the front end supports a subset of the kernel's LibraryLink interface. I'll be talking about that. To load dynamic libraries, that's how you modularly extend things. And this allows us to access certain libraries, which I won't talk about in here. No one cares about the abstract. I'm moving on. Okay. So one little known secret is that the front end has its own version of a Wolfram language evaluator. It's a secret. So don't tell anybody. The main purpose of this is to reduce inter-process communication. So as you may know, when you go to send something to be evaluated, it goes to the Wolfram kernel, and that requires it to be serialized, goes on to WSTP, aka MathLink, where it's then deserialized on that end. It does some evaluation, it does some computation, and then it goes and passes the result back through MathLink. And that's well and good for shift inter evaluations. But when we're working with a user interface where we need to be efficient, we have to be snappy, and we have to be responsive, we have to minimize those sorts of inter-process communications wherever we can. And so that's where we use the front end's Wolfram language evaluator. Now, that's not the only place that we use it. We also use it to have a nice, easy, top-level Wolfram language access point to questions that really only a front end is able to resolve. So one question might be something like, here I've got this string, right? But I need to know how long that string or how wide that string is going to be in screen points or ems. We can do that. We ask the front end how to do that. And I will evaluate this. And you see that it tells you that when we ask the front end using the front end evaluator, how long is the string Wolfram? It tells us it's 43 points or about 4 ems. Now, there's also a neat little thing here. If you want to try to get into the front-end evaluator, you can do so through FE backtick evaluate, which you may find a useful thing for testing. The front-end evaluator is what we use to evaluate expressions initially that belong to UI constructs, such as the button function in the button box. Now, of course, the front-end evaluator has limitations. Our goal isn't to go and just completely re-implement the kernel, but inside the front end. That would be crazy, and it would defeat what our purposes really are, which is just minimizing IPC. So what the front-end evaluator does, it's very important that anytime we do an evaluation that we're going to be short-circuiting the kernel, that what's evaluated will get exactly the same result that the kernel would. If we can't be certain that we can do exactly what the kernel did, we have to bail out and pass it to the kernel. So yeah, so that means the front end, we can perform like simple addition. If you give me a machine number and you give me another machine number, the front end will go, you know what, I do know how to add machine numbers. If you tell it plot, nah, it's not happening. Sorry, we're not going to be doing plot. We're not going to be doing ND solve. In fact, if you give me a number and something that is nominally a number, but we don't quite recognize it, it's off. We're not doing that. That's a job for the kernel, okay? So when the front-end evaluator can't perform an evaluation, it checks to see if there is an available kernel, and if there is one, it then passes it to the kernel to be evaluated. One other big limitation is that the front-end evaluator does not support first-class functions. So by first-class function, I mean this is something that we can write, we can pass it around, right? There's an evaluation semantics in the Wolfram language, you understand. You can take a symbol that is representing that function, you can then put brackets next to it, and that function will be applied to those arguments. The front end isn't going to be able to do that. This evaluator won't know that. What it can do, if it knows that head already, if we've already gotten some actually low level, some C++ code that's able to recognize that head, then we can perform that evaluation. Otherwise, we go, sorry, that's a problem for the kernel. Now, sometimes we have partial support for kernel functions. We know that we can do, we know we can do it kind of. And we want to make sure that in those, in some cases, we're like, we know we can kind of do this and it's going to be all right that we can kind of do it. An example like if, for example, we can have FE private backtick if. And what that will do is say, I'm accepting the risks. I know this may not be exactly what the kernel does, but in the way we plan to use it, it'll be all right. So please stay in the front-end evaluator. Yes, I do not. I'm sorry, but I do not have that. It is an what I will tell you, it is an ever-changing list. So we add new heads to the evaluator as we have need for them. So where there's a place we see that we can make an improvement, where we can reduce IPC without affecting the integrity of our evaluations, and there's a need, we will add it. Well, one way is to look at what link traffic looks like. Okay, so one way to know whether or not you are staying within the front end is going to be to look at the link traffic, which is exactly what I'm going to show in my demo. So here's an example. It's just as I was talking about. Here's an example. So I'm going to leave full screen. And I have an example notebook here. And my first example, I'm going to create a button, very creatively titled Click Me. And what it's going to do is it's going to look to see if I'm holding the Shift key. And if I am, it's going to set the evaluation cell's background to be, does anyone know what RGB001 will be? Without me clicking it, what is that going to be? Blue. And RGB111 will be white. Very good. So I'm going to evaluate, and something's going to happen here. I'm using Link Snooper. So what you're going to see here is all the link traffic for me doing that evaluation. I'll go ahead and clear that. That's just kind of like boilerplate to get it set up. Now, when I click, you'll see here that we have to have quite a bit of kernel traffic to figure out what to do with that button function when I clicked it. And I will show, there's the blue, there's white again, just holding the Shift key down. Ideally, when we're working with a UI element, we would like to not have to do all this communication with the kernel just to handle a button click. Imagine that this is in, say, your toolbar up here. You don't necessarily want to spend all of your time talking to the kernel to figure out how to change the font in a cell. So here's another one. It's a very small change. We've said, no, I really want if to stay in the front end. Okay, so I said I'm using FE private backtick if, and I'm using FE private backtick set. I want you to stay in the front end. Now, when I evaluate this, it's of course going to be traffic because I'm doing a shift enter evaluation. In your real user interfaces, that button will already be there. You're not going to need to do an evaluation to get a hold of it. I'm going to clear. Now let's look. I'm going to click. Oh, I click, click, click. No link traffic. Everything there is happening entirely within the front end process. Or in other words, lookma, no kernel. So I don't know what our evaluation semantics necessarily for FE private backtick if, because I'd have to look at the source, but I know who does know. Which is one way to test that you've got a problem with things not evaluated, that shouldn't be using FE private backtick, because that expression, whatever you've written, it just isn't a thing that we can handle entirely in the front end. So moving back to the talk. LibraryLink. This is, I think, why everybody's here, because LibraryLink and the front end sound like two things that absolutely don't go together. But they do. Remember that so LibraryLink, what is LibraryLink? LibraryLink is a kernel feature that does two things. It provides a Wolfram language API for loading dynamic libraries and calling functions from that library at evaluation time. And it provides a protocol and calling convention for C language functions, allowing them to be called from Wolfram language evaluated in a kernel. And why is that nice? It's nice because it's a modular way of extending the capabilities of the kernel through dynamic libraries. Now, there's some examples of this. Examples include the ffmpeg library, which we load through the ffmpeg tools packlet. And another example that we use internally and is very useful is GitLink, which gives us access to the libgit2 dynamic library, which we use for source code management at Wolfram Research. Well, like I said, if we want this stuff to minimize IPC, we need to do some of these tasks from within the front end itself. And to do that, we have LibraryLink in the front end. So the LibraryLink in the front end is not a fully complete version of LibraryLink as it lives in the kernel. What happens is that, generally speaking, somebody comes up to me and says, we need support for a numeric array for the video player, hypothetically. All right. And so then I get to work and say, all right, what can we do to actually support those features from within the front end? And then I implement them. So we don't implement everything that exists. We implement what we need as we need it. So right now, what that means is that we can load any dynamic library that the kernel can load. You compile it once. You compile your LibraryLink library once. It can be loaded into the kernel. It can be loaded into the front end. Both work. The only difference is that actually the front end's a little more strict about proper formatting of it. I'll talk about that in a little bit when I get to the example. We have support for the m-argument calling convention. So if you're familiar with LibraryLink, you know that one way of setting up a LibraryLink function is to have pass an array of m-arguments. We have support for that. The other calling convention is to have an m-link, a math link or WSTP link argument, which is both the input and the output, and the information gets serialized to that link. We support that as well. So for example, our video player uses the m-argument calling convention. GitLink uses the m-link calling convention. We have support for both. In terms of LibraryLink management modes, if you've worked with it, you've worked with m-tensors, or you've worked with m-numeric array or m-image, you know that there are several different memory management types: manual, shared. If you're familiar with LibraryLink, you're familiar with those different forms. We support all of the constants, one of them. We support all of those except shared. And the reason for shared is slightly technical, but additionally, in my search of source code, I found nobody using the shared type, so I didn't implement it. We support integer, real, and string. Complex isn't supported only because no one's asked me to do it. If we needed support for complex m arguments, I can add that in. M-tensor isn't there in 13.1, but it is coming. I actually have that in a branch, and it's on the way. Our support for m-numeric array is nearly complete. The only thing that it doesn't do is type conversions. So sometimes if you have an m-numeric array that's a type of, if it's 32-bit int, the kernel is able to convert that to 16-bit int if you ask it. I don't have that implemented yet, but that's again because nobody's asked me to do it. We don't have support yet for m-sparse array, m-image, and there's some other things that I think somewhat lesser used features of LibraryLink, such as the Library Expression Manager, Library Callback Manager, and the Wolfram Compile library that aren't implemented in the front end. So we have roughly, I would say, 50% support in the front end of what the kernel can do in LibraryLink. If you're going to call them, these are the only differences. Basically, take everything the kernel does, put it in the FE private backtick context. This way, we know that you're trying to load this library into the front end process and not into the kernel. Because of course, we have to specify that, right? There are two differences. We have FE private backtick library function apply. Can anyone guess why we need to have a library function apply? Why do we have to worry about that in the front end evaluator? I think Itai knows. Exactly. Yes. So we have to say what function we want, and we have to pass a list of arguments to it. And there isn't a direct equivalent to manage library information. That function, what it does is it allows us to list all of the dynamic libraries that the front end has loaded, as well as any functions that's loaded, so we can see what the status of them are. It was mostly a useful debugging tool. Okay, so I'm going to show another example. In this example, we're going to have buttons again, but this time they're going to use LibraryLink. Now, I'll point out, when you're debugging a LibraryLink library that you plan to use in the front end, debug it in the kernel first. because you're using the front end as your IDE. You don't want to be testing your library and have it crash your IDE. All right, so good idea to run them in the kernel. Kernels are disposable. So here we're going to load some libraries. Now I'm here loading them from LibraryLink, and you'll see, of course, traffic. It's fine. There's going to be traffic everywhere. I'm loading here a file called my file size and my file permissions, and I'm also going to load them into the front end. And I will show you that we've loaded them into the front end by calling manage library information. And you'll see there that we have this file status library, and we've loaded some functions out of it. Now, what are those functions? Let me show you. Oh, I'm sorry. Let me do that. Is that good? Okay. And oh, that was a bug report. You weren't supposed to look at that. Okay. So this is an example of LibraryLink, and let me see if I can embiggen this at all in Xcode, which is not a thing I normally do. Okay. So in LibraryLink, one of the things you need to do is you need to define these three functions. You'll see here that we have a Wolfram library get version, Wolfram library initialize, and Wolfram library uninitialize. When we are loading a library, we check for the existence of these three symbols, and that tells us that we have a LibraryLink library. If those symbols aren't there, it is not a well-formed LibraryLink library. And now here's an example of a LibraryLink function. So I would call this library statlink, because what it does is it provides a wrapper around the POSIX stat function, which gives us information about files that goes back to BSD, who knows, incredibly low number. But the important thing is it allows us to go to the file system and get interesting information about a file. One of the things that it does, we're going here, we're grabbing the M argument, which is a string. The string happens to be a file path. We pass that to stat. We have to get rid of it, or we have to get rid of that string. We're going to have a memory leak. Then we check to make sure the stat worked. And if it did, we go ahead, we grab, in this case, the size, stick it into an integer, and pass that back. Okay. This code works in the kernel. It works in the front end. And in my example, there's a few others. We can get file access time. We can get file permissions. It's all the same idea. We're just wrapping some code around stat and then passing them back in a form that the Wolfram language understands. So we'll get back to this. In this example, we have two buttons. Our first button will go ahead and it will update the cell tag of the cell with the button with the file size, and with the other one with permissions. And this is the naively implemented version, which I will clear. I click file size. You'll see we get a bunch of traffic, but it does update the cell tag. Now you may say, why is that important, updating the cell tag? Well, we do a lot of that in the front end, okay? Because that's where we keep a lot of information that's often hidden from the user. Here, I'm explicitly showing what the cell tags are, or permissions. And you see in this case, there's a lot of traffic for doing this. Now let's look at trying to do this using the front end. Same idea, file size, permissions, file size, permissions. Here we're getting the file size and the permissions of the actual notebook, putting that information in the actual cell. Because everything that is being done here is something the front-end evaluator knows how to do, including applying and calling that library function. And in that way, we've eliminated all of the IPC for that UI element. So those are pretty trivial examples. The most important example is the video player, which came in version 13.1. I think everybody's probably seen this demo by now of the video player. Using LibraryLink in the front end, we're able to get this video to run at about 30 frames per second versus about 15 frames per second or lower when it had to use IPC going through the kernel. In other words, it makes it usable in the front end, or it did until it stopped because we need to move on. The key thing about the player, I see we've got 2 minutes left, so very quickly, is the way this works is that we actually are able to, the library is actually able to spawn a thread from the front end that can work as a worker, but that worker thread isn't in any way interfering with the operation of the front end process itself because it's a separate thread. So we can in fact do multi-threaded work through LibraryLink. So the worker thread is the one that's out there going and decoding the frames from the video and the sound, and it's feeding them into a specific memory block and then notifying the front end that there's information to be had. Another function of that same library then reads out those frames and updates a raster box, has an ID, as a box ID for the raster box that contains that image, and it updates the information that's there. The advantage of that over the kernel is that we save on needing to go through a serialization and deserialization step at WSTP, and we avoid, I think, at least 3 memory copies as a process of this. And as a result, we're able to get a video player that actually runs pretty snappy. And now I got 30 seconds left. I want to acknowledge John and Lou for helping me with the examples and helping me get my understanding, I hope, as correct as I can get it for myself in this talk. Questions, 20 seconds. The video, I think, can actually go a little faster than that. So there are still many places for us to improve. So right now, the area that we would really like to improve is on those memory copies and making raster box snappier.